Hello and welcome to another video. In this video we're going to be working on shortest distance after road addition queries 1. And this one I've done already, so we're just going to do a review. So in this one you have an integer n and a 2D integer queries, and there's n cities labeled from 0 to n minus 1, and there's a path from the ith city to the I plus 1 city, so the initial graph starts like this. And then you have queries, and query basically adds an edge from one city to another. And then after the query, you want to calculate the shortest path from the 0 node to the n minus 1 node. And these edges stack on top of each other. So you want to return an answer where for each query you write the distance from 0 to n minus 1. So like in this example, for the first query, you're going to add this edge. And the shortest distance is 1, 2, 3. And also note that every edge is distance 1 here, because they basically tell you, like, I guess they don't tell you that, but yeah, essentially every edge is 1 in these examples. And so in query 2, you're going to add this. So the shortest distance is 1, 2. And then here you're going to add this. So the shortest distance is 1. And so when you add edges, like, they might make the path shorter, they might make it the same, but they're never going to make it longer, right? Because that's pretty easy to prove. Like if I have a graph and add an edge, I can just not use that edge. So my distance can never be longer. But it might always be shorter. So in this example, the first query adds this. So this is that case where this is one distance, and now I added this edge, and this didn't do anything. This is still 1. So the first thing you want to look for graph problems is the constraints. So you have n nodes and 500 queries. So essentially, a query adds an edge. So you can think like, I have n nodes and n plus m edges. Right, because essentially you have n edges to start, and then for every query you have another one. And then the other thing you want to think about is, are my edges weighted or unweighted? And they're unweighted. So if they're weighted, you're going to want to use Dijkstra's pretty much, because like in a weighted graph, you might take less edges, but it'll still take longer because an edge can have a high weight. But in an unweighted graph, it's basically, how do I traverse the minimum number of edges to get to the end, because they're all the same weight. So for no, you can just use BFS. So in this case, we have a no, so we can just use BFS. So like given a graph, like no matter how these edges are, how long would it take to do a BFS? And you want to think of these things before doing the algorithm. So like, if my graph has n nodes and n plus m edges, worst case, what's the runtime of BFS? So a BFS traverses every edge at most once. So it's just going to be n plus m for one traversal. And then I'm going to do this query amount of times. So this will be this. And if you look at the constraints, node is 500. This is 500. So this is 1k times 1k, which is 1,000,000, which is fine. So that's going to pass. So you could come up with something better maybe, but this at least gives you a solution. And I think I was trying to come up with something trickier, like maybe there's like some kind of caching you could do or something, like figure out if I add an edge, does this make it shorter? But it's kind of tricky because you're always going from 0 to the end. Like if you were going from some node to the end that's non-zero, like let's say here, and then you add an edge to a node before that node, then your distance doesn't change, right? Because you can't go backwards. So if I'm starting here and going here, and I add like this doesn't matter. But because I always start at 0, I'm always going to add an edge that can be used. So it's kind of tricky to figure out, like, how do we make this faster? And so this is actually a pretty good solution here, where we're just going to do BFS. And actually, Dijkstra's also passes. I think I originally did Dijkstra's and then realized I didn't need it. So Dijkstra's would just be a heap, and then this is still fine. Like basically, whenever BFS passes, Dijkstra's will almost always pass because you just add like a log factor, which is like nothing. It adds like 50 or something, or 20 or whatever. It's a very small number. Yeah. So essentially, we're just gonna do a BFS. So we're basic graph problem, right? Make a graph, and then for every query, add an edge, and then just BFS from 0 to n minus 1. So you should be able to make a graph with an adjacency list, and then add an edge to the graph, and then just do a BFS. And let's look at the code for that. So essentially, we make a graph. For every single node, we make an edge to the node afterwards, right? So for I less than n, we make a node to the one after. Yeah. I guess actually technically this should be n minus 1 because you don't want to make a node from n minus 1 to n because there is no node, but you're not going to use that anyway, so it doesn't really matter. Then we just get a result, which is the length of the queries. Then for every query, we're going to get the from and the to, and we're going to add that edge to the graph. Pretty simple. Then we're just going to call a BFS function to give us our result. And so the BFS is pretty standard. You make a queue, you add, there's a few ways to do this. One way is add the distance and the node, and then just do a normal BFS and have a visited set. Small trick you could do with BFS is whenever, so because BFS is FIFO, if I have some queue and I have some numbers and I put a number into the queue, let's say, and I'm trying to put another number in and that number is the same, because it's FIFO, if that number is already in the queue or processed, we never want to add it in because it'll never get there first. So if we add like another 3 here, this one will always happen first. So little small optimization you can make is instead of adding to the visited set when you pop, you can add to the visited set right when you add to the queue. So essentially, we just say if the node is the one we're looking for, we can return the distance. And let's go through all the children. If the children aren't visited, add them to the visited set right away and add them to the queue, because if they're in the queue or visited, we're never going to want to add them in again. Yeah. And then if nothing exists, return -1, but this should never basically be hit because there's always going to be a valid path, because there's already a valid path to start off. So we can run that guy. Yeah. And as far as runtime, it's not, Java's kind of inconsistent. Like if you use things with overhead, then it's slower. So I think probably an ideal solution like this graph, because you have n nodes, you probably want to just use like an array of nodes and an array of edges or something like that, or like a list. Like you basically want to minimize overhead with these hash maps and array lists. And so it'll have better runtime if you don't use a graph, but I mean, time complexity is still the same. Okay, so yeah, so let's go over time complexity in every step, I guess. So to make the graph, this is n time, and then for each query, we're going to add an edge, which is 01, and we're going to calculate BFS. And so like I said, BFS is going to depend on the number of edges. And the number of edges, worst case, is n plus m. So we're going to have, for every query, this can be n plus m. If n is the number of nodes and m is the number of queries. And space, so we can go through it again. So this graph is going to be linear, because for every node, you're going to have one edge. And then result doesn't count. And then for every query, we're going to add one edge. So that'll be m. And so basically, in BFS also, we're going to process every edge. So I think the graph is going to be the bottleneck here, and I think it'll just be n plus m here, essentially. Yeah, and I think that's going to be all for this one. So big things to remember. If your edges have no weight, use BFS. If your edges have a weight, use Jigsaws. And yeah, just know like shortest path, straightforward stuff. And then yeah, these tricks that I showed you with like the visited set faster and stuff. Yeah, it's going to be all for this one. If you did like it, please like the video and subscribe to the channel, and I'll see you in the next one. Thanks for watching.